Yesterday we talked about arithmetic, sequences, and series. An arithmetic sequence was one where we added something every time or subtracted. Today we're going to talk about geometric sequences and series. Now, geometric sequences and series are ones where you multiply by the same number every time. So let's read the definition together here. It says a geometric sequence is a sequence in which each term after the first is obtained by multiplying the previous term by a fixed non-zero constant. The amount by which we multiply is the common ratio, and we use an R for that usually. Common difference, we use a D. Common ratio, we use an R. So a very simple example of a geometric sequence would be 2, 4, 8, 16, 32, 64, and so on. Obviously here we're multiplying by 2 each time. Our first term was 2 and we multiplied every term after that by 2 to get our number. So one thing they may ask is find the first 6 terms of a sequence, let's say of a geometric sequence, given A1 is equal to 6 and R, the common ratio, is equal to 1/3. So this means we're going to start with a 6 and multiply it by 1/3 and keep doing that for 6 times. So 6 times 1/3 is 2. 2 times 1/3 is 2/3. 2/3 times 1/3 is 2/9. 2/9 times 1/3 is 2/27. 2/27 times 1/3 is 2/81. And I believe that is 6 terms. So it's very simple. It's similar to the arithmetic sequence. It's just with arithmetic, you're adding. With geometric, you're multiplying. That's the only difference. Okay, let's look now at the general forms of these equations. So first, the explicit form for geometric. It's an equals r, nope, sorry, an equals a1 times r to the n minus 1. So a1 times your common ratio raised to the n minus 1. That's the explicit form, and that's what we'll use most often. But just in case you need it, the recursive form is going to be a1, and then they give that to you, and then an equals r times an minus 1, for n is greater than or equal to 2. So those are the general forms for geometric sequences, the explicit form and the recursive form. Alright, so let's see how we can apply that. Let's say they wanted us to find the 8th term of a geometric series whose a1 equals -4 and whose common ratio, or r, equals -2. So let's use the explicit form. There's really no reason to use the recursive because then we'd have to do it like 8 times just to get that 8th term. That's the benefit of the explicit form. You can find any term you want. So I want to find the 8th term. So my a1 is -4, my r is -2, and then I plug in 8 for n. Okay, so you can plug that in your calculator. -4 times -2 raised to the 8 minus 1. And you get 512. So that's all there is to it. As long as you know your first term and your common ratio, then it's very simple to just convert to the explicit form and go from there. Okay, now they may also ask you to find the explicit form just giving you the sequence, and let me show you what I mean. Let's say they wanted us to find the 18th term of, let's do 2, -8, 32, -128, and so on. So they don't explicitly come out and tell you what the first term is and what the common ratio is, but it should be fairly simple to look at that and tell. Remember, the explicit form is an equals a1 times r to the n minus 1. Okay, well, you can look at that and tell that your first term is 2, and hopefully it doesn't take too much for you to figure out that the common ratio is -4. The way to get from 2 to -8 is to multiply by -4. So that would be our generic explicit form, and then we put 18 in to find the 18th term. Okay, so we can plug that in the calculator. 2 times -4. Make sure you put that in parentheses, just like I have it, raised to the 18 minus 1. You get a rather large number. It's something like -3.4 billion, or yeah, I think it's billion. But I'll just write it like the calculator says it, -3.435 times 10 to the 10th. Anytime you see that capital E in your calculator, it's just using scientific notation, so that means times 10 to the 10th. Okay, and the last thing we need to talk about is finding the sum. So let's find the sum of this sequence. Find the sum of the first 18 terms of the above sequence. So please make sure you read things carefully. Our first example just wanted to know what the 18th term was. Just wanted to know, if you list out the numbers, what is that 18th number? This is asking us to add up all of those 18 numbers. If you remember, when we want to find a sum, that's called the series, and we can use sigma for that. So since we want to find the first 18 terms, I'm going to put 1 at the bottom and 18 at the top. This will tell my calculator to do the first 18 terms because I do 1 through 18. And then I just put the explicit form in right here. So 2 times -4 raised to the n minus 1. And then you can plug that in your calculator. And I'm going to pull that up for us so we can look at it. Okay, so remember, this calculator doesn't have the summation that many of your calculators do. If yours has the summation, you just go to Math 0, plug it in exactly like it looks here. If you don't, then you need to go to Second Stat, go over to Math, the fifth one down is Sum, go to Second Stat again, go to the middle one, OPS, fifth one down is Sequence, because that's what a series is, it's the sum of the sequence. Then we plug in the equation, in this case it's 2 times parentheses -4 raised to the parentheses x minus 1, close parentheses. So that's the equation. Then I have to do comma x, because I got to let the calculator know what variable I'm using. Then comma 1, that's the first number. Comma 18, that's the last number I want it to plug in. Close your parentheses and hit enter. And you see it's a rather big number, -2.7. Again, I think that's in the billion range, maybe 27 billion or something like that. But that's what you get, -2.748 times 10 to the 10th. So again, if you look at that, I showed you that that little capital E to the 10 just means times 10 to the 10th. Okay, the homework for this section is page 957, and it's number 2 through 36 even.